Well, welcome to video 4 for chapter 7. This video is called Machines and Efficiency. One of the ways that we can explore energy and its conservation is through learning about machines and how effective they are at getting work done. For any machine to do what it's supposed to do, energy has to be put into it. That energy is then used to accomplish tasks. Think of your car, for example, which is a complex machine. You put energy into it in the form of fossil fuels, and that energy gets used to make it move and heats the inside. The electrical energy that's stored in the battery is used to make the electrical systems work. A car is quite a complex machine, so when studying machines in a physics class, we look first at more simple machines. We want to find out that since all machines require an energy input, what happens to that energy as it goes into and through that machine? How can we get the most work out of a machine for the energy that we put into it? By the end of this video, you should have an understanding of simple machines and how conservation of energy plays a role in their use, how we determine the efficiency of a machine, and be able to compare and contrast energy and momentum in a collision. Now, in physics, we define a machine as a device that multiplies forces or changes the direction of forces. The underlying principle in all machines, though, is conservation of energy. One of the simplest machines is a lever, such as the one shown here. When you operate a lever, you push down on one end, and on the other end lifts up a heavier object. So you do work on one end, and the other end does work on a load. This changes the direction of the force that you apply. If you push down, the load is lifted up. In most cases, the amount of friction is small enough to be able to ignore it, so this results in the work input equaling the work output. Now, if you remember, since work equals force times distance, the input force times the input distance equals the output force times the output distance. All this means is the amount of work that we put in is going to equal the amount of work that we get out. So let's take a look at what the effect of this is. Okay, so on a lever, the point of support about which a lever rotates is called the fulcrum. So this here is a fulcrum. When the fulcrum is relatively close to the load, then a small input force will produce a large output force, like what's pictured here. Okay? Further away that a fulcrum is from the load, the greater amount of force that you would have to apply to the lever to lift that load. This is because when the input force is extended further away from the fulcrum, that input force is exerted through a larger distance, and the load is moved through a correspondingly short distance. What this means is, with a longer lever, you can multiply the force that you apply. But because no machine can multiply the work done or the energy used, the load moves through a shorter distance than the distance through which the input force is applied. Now, this can be experienced if you've ever had to jack up a car. By exerting a small force through a large distance, you can provide a large force that acts through a small distance. In this picture here, every time this girl pushes the jack handle down 25 centimeters, the car rises 100th as far, but with 100 times the force. She can apply a relatively small force to get a greater force on the car, but she has to apply her force through a greater distance than the car rises. However, the total amount of work that she does on the lever is equal to the amount of work that's done on the car. And all of this is completely in line with conservation of energy, right? Because work is nothing more than just a change in energy. So the amount of energy that we put in is equal to the amount of energy we get out. Now, another simple machine is called a pulley. When a string or a rope is placed over a single pulley, as in the picture here on the left, The pulley only changes the direction of the force. It does not multiply the force in this condition. So you'd have to pull down on this rope with an equal force of the weight of the object you're pulling up. The input force would equal the output force. However, when arranged as in this picture here on the right, the output force is doubled. The force applied to the load is increased, and the distance it's moved is decreased. For this pulley system here on the left, the distance that you pull the rope would be equal to the distance that the load is raised. While on this side over here, the amount of rope that you pull, or the distance that you pull that rope, is going to be greater than the distance that the load is raised, because we've doubled our input force. So some of the energy that's gone into, or the work that's gone into pulling on that rope, goes to multiplying that force and thereby decreasing the distance that the load is raised. What this is showing us is that, as with any machine, forces can change. The size of the forces can change, while work input and work output are unchanged. It's called a block and tackle system of pulleys, such as these shown here, multiply the force more than a single pulley can. In a block and tackle system, you have a fixed pulley and a movable pulley where you attach the load. You pull on this end and you've got more ropes pulling up on the load. So the force with which you're pulling down is multiplied on that load. So let's take, for example, this picture of this guy pulling here using a block and tackle system. Let's say he pulls 7 meters of rope with a force of 50 newtons. He lifts a 500 newton load, a vertical distance of, say, 0.7 meters. Now, our expression for work is force times distance. And we also define work as the change in energy. So if we multiply the force that he applies through the distance through which that force is applied, we find that the energy he uses is equal to 350 joules. Now, the load has a weight of 500 newtons, and it's lifted a distance of 0.7 meters. So this tells us that the potential energy gained by that load is 350 joules. The energy the man expends in pulling the rope is equal to the increased potential energy of the 500 Newton block. Energy is transferred from the man into that load. So any machine that multiplies force does so at the expense of distance. And likewise, any machine that multiplies distance, such as your forearm and your elbow, does so at the expense of force. No machine or device can put out more energy that's put into it. No machine can create energy. It can only transfer energy or transform it from one form to another. Now, each of the machines that we've just looked at are examples of simple machines. Other simple machines include like an inclined plane, a wedge, screw, wheel, and axle. And in each of these cases, they've also been the ideal case, so an ideal simple machine. And all that means is that 100% of the work input appeared as work output. In reality, that doesn't happen. Some of the energy that's transferred into a machine is transformed into a variety of other forms, and not all of it is available to do work on the load. Typically, this other form of energy is what we call thermal energy, which is really just the kinetic energy of the molecules within the machine. This makes the machine and its surroundings warmer. Now, sometimes we can recapture some of that thermal energy, such as like in your car or something on these cold months. When you heat your car, you're just taking the heat that is produced in the engine and pumping it back into the car. But still, a lot of that energy is left off into the environment. Now, since no machine can ever put out the same amount of energy that's put in, we have to have a way to talk about how effective a machine is. One of the ways we do this is through what is called efficiency. Now, even a machine as simple as a single lever is going to convert a small fraction of the input energy into thermal energy. There's friction in a lever right at the fulcrum right here. So some of the energy is going to go into thermal energy. We may do 100 joules of work and get out 98 joules of work from the machine. So we can say then that that lever is 98% efficient. Now, if say this girl doing the jack here puts in 100 joules of work and increases the potential energy of the car by 60 joules, well then that jack is only 60% efficient. 40 joules of her input work has been applied against friction, making its appearance as thermal energy. In a pulley system, a considerable fraction of input energy typically goes into thermal energy. So if we do 100 joules of work, the forces of friction acting through the distances through which that pulley turn and rub about their axles may dissipate 60 joules of energy as thermal energy. In that case, the work output is only 40 joules and the pulley system has an efficiency of 40%. The lower the efficiency of a machine, the greater the percentage of energy that's degraded to thermal energy. So inefficiency exists whenever energy in the world around us is transformed from one form to another. Efficiency then can be expressed by the ratio of the useful energy output over the total energy input. Basically what this is saying is our efficiency is equal to what we get out of our machine over what we put into our machine. We're always going to put in more energy than we get out, so we're always going to get an efficiency less than 1, so a percentage of the energy that we put into it. Another way to look at the inefficiency that accompanies transformations of energy is that in any transformation, there is a dilution of available useful energy. The amount of usable energy decreases with each transformation until there's nothing left but thermal energy at ordinary temperature. When we study thermodynamics later on, we're going to see that thermal energy is useless for doing work unless it can be transformed to a lower temperature. Once it reaches the lowest practical temperature, that of our environment, it cannot be used. The environment around us is kind of the graveyard of useful energy. But through the use of machines, we're able to take that energy and get some use out of it, but what we get out of it is always going to be less than what we put into it. So that covers machines and efficiency. You'll want to pay attention to a section of your reading packet titled Comparison of Kinetic Energy and Momentum. We'll see you in class.